Alright guys, so today we are actually combining the conversions that we've learned the past two class periods together. And so today we're actually going to combine grams to moles to particles, or particles to moles to grams. Now, so the unit mole is used as kind of like a layover in converting from grams to particles or particles to grams. So going back to, say, the dozen example, if I have a dozen gumballs and a dozen ping pong balls, I have 12 of each. So 1 dozen equals 12 of each. Ping pong, gumballs, it doesn't matter. So that's the same with the mole, is always 602 sectillion particles. It doesn't matter what I'm looking at. The mole is always going to be 602 septillion particles. Now, if I have a dozen ping pong balls and a dozen gumballs, they are going to weigh differently. I have the same number of each, but they are going to weigh differently because they're made of different things. That is the molar mass. So 1 dozen ping pong balls may weigh, 50 grams, and a dozen gumballs may weigh 100 grams. I still have 12 of each, but they weigh differently because they're made of different things. And that's the same with molar mass. I may have the same number of particles, but those particles are going to weigh differently depending on what type of elements that I have with them. So we're going to use both of these to convert between, if I have so many grams of something, how many atoms of something I have. If I have so many molecules of something, how many grams does it weigh? And so we can use them all, like I said, like a layover. So say I'm flying to, Ontario, Canada, and there's not a direct flight to Ontario, Canada from Dallas. Say I have to fly through Chicago. So you would fly from Dallas to Chicago and then Chicago to Ontario, okay? Now, that's the same with the mole, okay? The mole is like a layover. So if I'm going from molecules to grams, I have to go through the mole. There's not a direct conversion between. I have to go from molecules to moles using Avogadro's number, and moles to grams using the molar mass. Okay? So, my first example says, how many atoms are in a pure iron nail that has a mass of 13.2 grams? Okay? So, first thing I'm looking at is my given unit. My given unit is grams. Okay, when I see the unit grams, I should think molar mass. Okay, if I see the unit grams, I should think I need to use molar mass in my conversion. Now, what is it asking for? It's asking for atoms. When I see atoms, I should think Avogadro's number. Okay, I should think 602 sectillion, or 6.02 times 10 to the 23rd. Now, notice one thing. Notice my given unit and my needed unit are not moles. What you have to do is you have to convert through the mole. So I'm starting with grams. I'm going to have to convert from grams to moles. From grams to moles, using that molar mass. 1 mole is equal to the molar mass. In this case, it's the molar mass of iron. Okay. Then I'm going to convert from moles to atoms using Avogadro's number. Okay, equals that 602 septillion. Okay. So, again, we can't go directly from grams to atoms. We have to go through the mole to get there. Okay, so the formula of our compound, this is pure iron. This means it's just iron. Okay, so to find the molar mass of iron is pretty easy. Just look at the periodic table. On your periodic table, iron says 55.85. So that means that the molar mass of iron, 1 mole of iron, weighs 55.85 grams. Okay, so I got that from my periodic table. Now, there's one more conversion that I'm going to need, because this gets me to moles, right? but I need to go from moles to atoms, so I have one more conversion that I'm going to use. I'm just going to put it off to the side. Is Avogadro's number. 1 mole is 6.02 times 10 to the 23rd atoms. Okay. So those are the two conversions I'm using. So I'm using two conversions, which means when I set up my T-chart, I'm going to draw two lines. Okay. So I'm starting off with 13.2 grams of iron. Okay. Now I see that there are grams on top, so I know that grams is going to go on the bottom. Okay. Grams of iron is going to go on the bottom. Molar mass of iron is 55.85. Okay. And that's how many grams are in 1 mole of iron. Now that gets me to moles of iron. It gets me from grams to moles, but again I need to go from moles to atoms. So I'm going to put 1 mole of iron on the bottom this time because again, what the unit on top is the unit on the bottom. What goes above goes below. And then on top of that, I'm going to put Avogadro's number because that is what I need. I'm looking for atoms. Okay. Now remember, what we do in these multi-steps, we multiply across the top. Okay, so we're going to do 13.2 grams. Okay, so 13.2 times 1 times Avogadro's number, 6.02, and again that E button, second E, 23. Okay, and so I get 7.95 because I got 3 sig figs in my given. So I'm rounding to 3 for my coefficient. But don't forget that times 10 to the 24th on top. And then 55.85 divided by, or times 1 is 55.85 on the bottom. So I'm just going to divide those. Divided by 55.85. Okay, so that's going to give me 1.42 times 10 to the 23rd atoms of iron. Okay, so that's going to be my answer there. Now let's look at the next example. It says, how many grams of sulfur tetrachloride does 6.25 times 10 to the 24th or 25th molecules contain? Okay, so in this case, what am I given? I'm given 6.25 times 10 to the 25th molecules. So again, I see molecules, I should think Avogadro's number. Okay? What is it asking for? It's asking for how many grams. When I see grams, I should think molar mass. And again, it's the molar mass of sulfur tetrachloride. Okay? Now again, there's not a direct conversion between molecules and grams. This example, we're going backwards. So we're starting with molecules, going from molecules to moles using Avogadro's number, and then moles to grams using the molar mass. Okay? So our first step is to find the formula of the compound. So we got sulfur tetrachloride. Okay? And it's given. The formula will be given to you. Okay? Now, that's 1 sulfur, 4 chlorines. So to calculate, we do 1 sulfur, which is 32.06, plus 4 chlorines, which is 35.45. And again, I got these numbers from my periodic table. Okay, on my periodic table, sulfur is 32.06, chlorine is 35.45. Okay, so when I do 32.06 plus 4 times 35.45, I'm going to get 173.86. 173.86 grams per mole. So what that means is 1 mole of sulfur tetrachloride weighs 173.86 grams. And again, this isn't the only conversion you're going to be using because we're starting with molecules. We're starting with molecules. We're going to have to also use Avogadro's number. 23rd. In this case, is molecules. Okay? So let's start our conversion. Again, there's two conversions, so we're using two lines. Start with your given, 6.25 times 10 to the 25th molecules. Okay. Now again, my unit on top is molecules. That means my unit on bottom is going to be molecules. Am I going to use the molar mass for that? No. My unit is molecules. I'm not using molar mass. I'm using Avogadro's number this time. So Avogadro's number is going on the bottom because my unit on top is molecules. And then on top of that is going to be 1 mole. Okay, and this is of sulfur tetrachloride. Okay. Now that gets me to moles, but again, I don't want moles. I want grams, so I got to use this one more conversion. So 1 mole of sulfur tetrachloride is going to go on the bottom, again, because moles is on top, so moles is on bottom. And then the molar mass, 173.86 grams, is going to go on top. Okay? And again, remember, the number 1 always goes with the mole, unit mole. Okay? You will never have another number in front of the unit mole. So please make sure that you never put the molar mass in front of the unit mole or Avogadro's number in front of the unit mole. Okay? So multiply across the top. So we have 6.25 times 10 to the 25th times 173.86. Okay. And that's going to give me 1.08665 times 10 to the 28th. So I'm going to do 1.09 times 10, or sorry, it's the 28th. 10 to the 28th divided by Avogadro's number on the bottom, because it's 6.02 times 10 to the 23rd times 1. So 6.02 times 10 to the 23rd. So divided by 6.02. Second E23. Okay. So that's going to give me, now my given has 3 sig figs, so I'm going to round my answer to 3. So it's 18,050. So I'm going to round that to 18,100 because 3 sig figs grams of sulfur tetrachloride. Okay. Grams of sulfur tetrachloride. Now, I'm going to skip the next two examples. If you want those examples, we have the key that you can check your work on that, but I'm going to move on to percent composition. Okay, so percent composition tells us the mass percent of each element in a compound. Okay, so basically what it tells us is if we say we have H2O, we have water, and I want to know what percentage of H2O's mass is hydrogen and what percentage of H2O's mass is oxygen. Okay, we can calculate that. Percent composition is actually a really good way to identify what type of compound we're looking at. Okay, we can use mass percent later on. You won't have to solve this, but they use mass percent to find out in forensic science. So say they have a sample of carpet and they don't know who the carpet's manufacturer are. They run it through this thing called a mass spectrometer, and they find the mass percent of each element in that carpet, and they can use that mass percent to find the formula of the compounds in the carpet, which can find the manufacturer. So we use percent composition. Percent composition is used a lot to identify different compounds. Okay. So to calculate percent composition, first you're going to write the chemical formula. Then you're going to calculate the molar mass of that chemical formula, of the entire chemical formula. Then it says divide the mass of each element. Now that's each element, the mass of each element in the formula. So in this case, if you were doing water, I wouldn't divide the mass of just one hydrogen, it'd be the mass of 2 hydrogens. So it'd be the mass of 2 hydrogens divided by, so that's over, the total mass of water. And then you're going to multiply it. It says write each one is a percent with two numbers past the decimal. So to do that, you would multiply that decimal that you get times 100 to get a percent. Okay, so let's do this. First one is 10,4-sulfide. So the formula of the compound, 10,4-sulfide, and again, it gives us the formula SnS2. Okay, so the mass of the compound. Now what I like to do is have the mass of each element and the mass of the compound in this work. So I have 10 in my compound, and I have sulfur in my compound. Okay, so the mass of 10, in my compound I only have one 10, and this is TIN, 10. Okay, if you look on the periodic table, it's 118.71. Okay, now the mass of sulfur, now there are two sulfurs, so what I have to do is multiply that mass by 2. Okay, the mass of sulfur, one sulfur is 32.06, but again, there's two sulfurs in my compound, so I got to do 2 times that. So the mass of sulfur in this compound is 64.12. Okay, so what I do is I take the total mass of 10 in the compound, 118.71, again, that's my 10, plus the total mass of sulfur in my compound, which is 64.12, that's my sulfur. Add that together, and I get 182.83. Okay, so this is the total mass of my compound. So to find the percent composition of each, I'm going to take the mass of the element in the compound, and divide it by the total mass of the compound, and then take that answer and multiply it by 100, and that will give me my percent. So for 10, my mass of 10 in the compound is 118.71 divided by the total mass, which is 182.83. Multiply that by 100, and you'll get 64, again, round to 2 decimal places. Okay, 2 decimal places. You'll get 64.93% 10. Okay, so what this means is almost 65% of my compound's mass is coming from my 10. So then we're going to do sulfur. So the mass of sulfur in my compound, 64.12, divided by the total mass of the compound, 182.83, times 100, and that's going to give me a percent mass of 35.07% sulfur. Okay, so 35% of my mass in my compound is sulfur, and 65% is tin. Okay, now let's look at the next example. It says, find the percent composition of ammonium chloride. Okay, ammonium chloride is NH4Cl. So I have one nitrogen. Notice ammonium is a polyatomic ion, but when I'm calculating percent comp, you've got to separate it out into its individual elements. We got nitrogen, hydrogen, chlorine. Okay, so we have one nitrogen, which is 14.01. Hydrogen, there are 4 hydrogens. Its mass is 1.01. So that gives me 4.04. Again, I got that 1.01 from the periodic table. And then I have one chlorine, 35.45. So I take these and add them together. 14.01, which is nitrogen, plus 4.04, which is hydrogen, plus 35.45, which is our chlorine. Okay, add those together, my mass is 53.30. Okay, so again, now we're going to calculate the percent of each element. So we take the mass of the element in the compound divided by the total mass. So the mass of my element in my compound for nitrogen, 14.01, divided by the total mass, which is 53.30, times 100. So that's going to give me 26.29% nitrogen, So again, that means 26% of my mass in ammonium chloride is nitrogen. Then for hydrogen, the mass of hydrogen in ammonium chloride, which is 4.04, divided by the total mass, which is 53.30 times 100, and that's going to give me 7.58% hydrogen. And then my last one is chlorine. So the mass of chlorine, 35.45, divided by the total mass, 53.30 times 100, and that is going to give me 66.51% chlorine. So if I asked you what makes up most of the mass in ammonium chloride, you would say chlorine. Chlorine makes up most of the mass. It makes up almost 67% of the mass of ammonium chloride because it has the highest percent mass in ammonium chloride. Okay? So that's how you calculate mass percent. It's not necessarily that hard. You just have to remember that formula. The mass of the element in the compound divided by the total mass of the compound times 100. And that's how you find, and you got to go through every single element. Even if there's a polyatomic ion, you split that polyatomic ion up to find your mass percent.